In the most remote wilderness on Earth, where temperatures plunge to -40 degrees and sunlight vanishes for months at a time, something impossible bleeds from the ice. A 5-story waterfall of blood-red liquid cascading down the face of Taylor Glacier, staining the pristine white ice like an open wound. For over a century, bloodfalls has defied explanation. And when scientists finally discovered what was really happening here, the truth turned out to be far stranger than anyone imagined. This is the story of how a geological mystery became a window into alien worlds and changed our understanding of where life can exist in the universe. The McMurdo Dry Valleys, Antarctica's most extreme desert and the closest thing to Mars on Earth. The surface of these valleys is a place of haunting desolation. Scattered across the floor are the mummified remains of seals, preserved for centuries by the freezing winds, silent witnesses to a landscape that seems entirely hostile to life. It is a frozen graveyard where the rules of nature appear to have reached their limit. In 1911, British geologist Thomas Griffith Taylor led an expedition into these valleys during Robert Falcon Scott's ill-fated Terra Nova expedition. What Taylor discovered at the tongue of what he initially called the first glacier stopped him in his tracks. A massive stain of deep red spreading across the ice face, with liquid actively flowing from beneath the glacier. The color was unmistakable, the deep crimson of blood. But this was Antarctica. No mammals, no birds nesting nearby. Nothing that could bleed on this scale. Taylor proposed what seemed like the only logical explanation: red algae, microscopic organisms tinting the water as they bloomed in the meltwater. But there was a problem that would take nearly a century to solve. Beyond the startling red of bloodfalls lay a deeper, more unsettling defiance of nature. When researchers finally conducted detailed chemical analysis of the bloodfall's water in the 1960s and 70s, they discovered something that made the algae hypothesis impossible. The water was hypersaline, nearly 4 times saltier than seawater. Salt concentrations are so extreme that nothing should be able to live in it. But where did all this salt come from? Millions of years ago, the McMurdo Dry Valleys weren't a frozen desert. They were fjords, flooded by the sea. As the climate changed and sea levels dropped, a pool of ancient seawater became trapped. Then, as the Taylor Glacier advanced over this pocket, something remarkable happened: cryoconcentration. As pure water froze onto the bottom of the glacier, the remaining liquid became saltier and saltier. The salts and minerals squeezed into an ever smaller volume. What started as seawater became a brine 4 times more concentrated. No algae could survive in that brine. In fact, the water was so salty it shouldn't even be liquid at Antarctic temperatures. It should be frozen solid. Yet here it was, flowing freely at -5 degrees Celsius. The salt acted as antifreeze, keeping the water liquid far below its normal freezing point. But there's more to it than just salt. It's a geological paradox. The very act of the water trying to freeze releases enough heat to keep the rest of the liquid moving. As the brine begins to freeze, it releases latent heat, warming the surrounding ice just enough to keep the veins and channels inside the glacier open. The glacier is essentially keeping its own plumbing warm. So, if not algae, what was making the water red? The answer seemed simple: iron. The water was loaded with dissolved iron, and when it contacted oxygen in the air, it rusted instantly, like blood oxidizing when exposed to air. But where was this iron coming from? Beginning in 2004, glaciologist Jill McCookie, now at the University of Tennessee, led a decade-long investigation that culminated in 2014 when her team finally drilled into the Taylor Glacier. By tapping into the glacier's internal plumbing, they extracted samples of pressurized brine, revealing an ancient chemical composition hidden within the ice. What they found was evidence of something hidden beneath the ice, something that had been there for an unimaginable length of time. Using an airborne electromagnetic sensor, the team mapped a massive subglacial feature, a lake of liquid water trapped beneath 400 meters of solid ice. a lake that had been sealed off from the atmosphere, from sunlight, from the surface world, for at least 1.5 million years. This water is chemically pure from the perspective of time. It contains zero traces of the modern world, no industrial chemicals, no modern atmosphere, no isotopes from nuclear testing. It is quite literally a bubble of the Pliocene epoch preserved in the 21st century. Far from a mere surface phenomenon, Blood Falls serves as a rare window into an ancient, isolated ecosystem. And when scientists finally analyzed what was living in that water, they realized they'd discovered something that shouldn't exist. In 2009, Jill Mikuki published findings in the journal Science that would revolutionize our understanding of extreme life on Earth. Her team had successfully cultured microorganisms from the Blood Falls water, bacteria that had been isolated from the rest of the biosphere for over 1 million years. These extraordinary bacteria thrive in conditions that violate nearly every established rule of biology. Nearly all life on Earth depends on photosynthesis, sunlight converted to energy. But beneath Taylor Glacier, there has been no sunlight for 1.5 million years. Whatever was living down there had to find another way. The bacteria in Blood Falls don't photosynthesize. Instead, they practice something called chemosynthesis, deriving energy from chemical reactions. In the total darkness beneath the ice, these microbes have swapped oxygen for iron. They breathe the minerals in the rock to fuel their existence, essentially living off the chemistry of the Earth itself. But where does that iron come from? The glacier itself is a giant mill, grinding the bedrock into a fine powder, rock flour, as its massive weight moves across the valley floor. But it's more than just grinding. The microbes are actively mining the iron from the dust beneath them. This is a lithotrophic ecosystem, literally rock-eating. The boundary between geology and biology has blurred until they are essentially the same process. The microbes don't just live on the rock, they are an engine in the rock's chemical cycle, turning a static tomb into a functioning factory. As the bacteria metabolize the iron in the rock, they convert it into a soluble, colorless form that dissolves into the trapped brine. For millions of years, this water remains clear, hidden in the pressurized dark. But when it finally escapes through fissures in the glacier and hits the air, it contacts oxygen for the first time in over 1 million years. The dissolved iron instantly oxidizes. It rusts in an instant. The clear water turns blood red in seconds. In this world of zero sunlight, waste is a luxury they cannot afford. These species have evolved to recycle their own chemical byproducts, creating a perfect closed-loop ecosystem where every nutrient is exchanged in a delicate balance. It is a community that sustains itself entirely on its own recycled history. By using radio echo sounding, essentially ice-penetrating radar, they finally mapped the glacier's hidden plumbing, revealing a network of liquid brine that shouldn't exist in such extreme cold. They mapped the entire subglacial hydrological network, the system of channels and reservoirs beneath Taylor Glacier. The radar revealed a vast, interconnected system. This subglacial reservoir feeds into multiple channels that snake through the bedrock beneath the glacier, an aquifer that may extend for kilometers beneath the dry valleys, a dark kingdom much larger than a single lake. Driven by the immense pressure of the ice above, this brine periodically forces its way through cracks in the glacier, erupting at Blood Falls. This explains why the flow isn't constant. It pulses, sometimes surging, sometimes trickling. But even today, we don't fully understand what triggers these pulses. Is it internal pressure as the glacier shifts, or complex siphon effects within the subglacial plumbing? The episodic nature of Blood Falls remains an enduring mystery. But perhaps the most profound implication of this site has nothing to do with Earth at all. In 2015, researchers drawing on this discovery published parallels between the Blood Falls ecosystem and the potential for life on Europa, Jupiter's icy moon. Like the Taylor Glacier, Europa's global ocean has been isolated from sunlight for eons, in contact with a rocky seafloor that could provide the iron and sulfur needed for life. If life can thrive in the darkness beneath Antarctic ice, sustained by nothing but chemistry, then it can thrive in the darkness beneath the ice of another world. Blood Falls is no longer just a geological curiosity, it is a blueprint for finding life beyond Earth. So what is Blood Falls really? It's the visible outlet of an ancient subglacial ecosystem, a community of microorganisms that has survived in complete darkness and isolation for at least 1.5 million years, possibly much longer. The ecosystem is powered not by sunlight, but by chemical energy derived from iron and sulfur reactions. The bacteria metabolize iron, converting it from insoluble rust to soluble ferrous iron. This iron-rich water, kept liquid by extreme salinity, flows under pressure through channels in the bedrock. When it finally breaches the glacier face at Blood Falls, it contacts oxygen and instantly oxidizes, turning the water the color of blood. The red color that terrified early explorers isn't blood, isn't algae, isn't a mystery. It's rust, ancient iron, cycled through bacterial metabolism, oxidizing in real time. These microorganisms represent a form of life that doesn't depend on the sun, practicing a metabolism that predates photosynthesis by billions of years, a living connection to Earth's ancient past. The discovery has spawned ongoing research programs. Teams from the University of Tennessee, Montana State University, NASA's Jet Propulsion Laboratory, and institutions around the world continue to study blood falls. Over the last decade, researchers successfully cultured several species from blood falls in laboratory conditions, allowing for detailed study of their metabolic processes. The findings continue to surprise. These organisms can survive for millions of years in a state of suspended animation, slowing their metabolism to a crawl while withstanding salt concentrations and temperatures that would be lethal to most Earth life. Blood Falls has taught us that life is more resilient, more adaptable, and more creative than we ever imagined. But for all we've learned, profound mysteries remain. We still don't know the full extent of this hidden world. The true size and depth of the reservoir beneath the Taylor Glacier remains uncertain, and we've likely cultured only a fraction of the biodiversity hidden in its depths. Even its age is a mystery. 1.5 million years is the minimum, but this ecosystem could have been isolated for 5 million years or more. Perhaps most intriguingly, is Blood Falls unique? Antarctica contains over 400 known subglacial lakes, each a potential time capsule of its own. The implications extend far beyond our planet. If life can persist in the darkness beneath the Taylor Glacier, then the subsurface oceans of Europa and Enceladus become prime targets in the search for extraterrestrial life. Even Mars, with its ancient ice, becomes more promising. If life once existed there, could it still survive in isolated pockets beneath the surface, sustained by chemistry rather than sunlight? Blood Falls has fundamentally changed the equation for where we search for life in the universe. It proves that sometimes the most profound discoveries come not from looking up at the stars, but from looking down at the ice beneath our feet. If you enjoyed this journey into one of Earth's strangest mysteries, let us know in the comments what phenomenon you'd like us to investigate next. And don't forget to like, comment, and subscribe to join us as we explore the mysteries hidden in our own planet.